Hi, let's look at today the concept of work. Let's start with this.
These barbells have a mass of 120 kilograms. Since they are resting on the surface of the planet Earth, we know that the force of gravity acting on them is about 10 times that number of newtons. It takes a very strong man to lift something that weighs so much. Because if the barbell is being pulled down by a force of 1,200 newtons, it must take 1,200 newtons of force to hold it up. Of course, if we were on the moon, where the force of gravity is only 1/6 that of the Earth, anybody can do it. But we're not on the moon. That looks like hard work. But how much work? 1,200 newtons worth? To lift the barbell? How far? Exactly 2 meters. But what if you only lifted the barbell half that distance, say 1 meter? Surely that doesn't take as much work as lifting the barbell 2 meters. When you lift the barbell all the way up, you're doing 1,200 newtons times 2 meters worth of work. When you lift it only halfway up, you're doing half that amount of work. 1,200 newtons times 1 meter. In fact, this is how you measure work in physics. Work equals force times distance. Here you're doing 1,200 newton meters of work. And here you're doing 2,400 newton meters of work. That's simple enough. But suppose that after the show, the strong man discovers that his car is stuck in the mud. He pushes it and pushes it, but it won't budge a millimeter. And suppose that at the very same time, the clown, who hasn't got a car, is in the act of picking up the telephone to call a cab. Which of them would you say is doing work at this particular moment? The strong man or the clown? The clown. Because work equals force times distance. And although the telephone receiver only weighs about 2 newtons, while the strong man's car weighs perhaps 15,000 newtons, when he lifts the telephone receiver, the clown is applying a force of 2 newtons through a distance of 50 centimeters, let's say, or half a meter. And therefore, he's doing 2 newtons times half a meter of work, which is 1 newton meter of work. The strong man, on the other hand, may be exerting thousands of newtons of force. But since the car is not moving, there's no distance involved, and the poor man isn't doing any work at all. A force of even thousands of newtons times 0 distance equals 0 work, whereas a force of only 2 newtons through a distance of only half a meter does equal some work, even if it's only 1 newton meter worth.
So let's talk more about the concept of work as I pull up my PowerPoint slides. By definition then, in physics, work is the amount of energy transferred by a force through a certain distance. Whoops. And in Canada, we're on the metric system, so this is in joules. Our unit of work is joules. In order for it to be in joules, these have to be in Newton meters. So 1 joule, 1 J is equal to 1 Newton meter. So if we look at this picture with the box here, the box is moving nowhere, but we're exerting a 10 Newton force on the box. So how much work would be done? Well, if we use our formula, that's 10 times 0, because there's no movement. So how much work? 0 J, 0 joules, because the box didn't move. However, let's look at this picture. Here we have a lever, and we're pushing down on the lever on the left side, and the box is coming up on the right. The box is 10 newtons. That's our output. Our input is only 5 newtons of force. When we push down, we push a distance of 2 meters, and the box on this side comes up 1 meter. So let's calculate the amount of work on both sides of this lever. So what's our force on this side? 5 newtons times a distance of 2 meters. And so the amount of work done on this side is 10 joules. How about on this side? Well, the force of the box is 10 newtons, and it only came up a distance of 1 meter. What do you notice about the amount of work on both sides of this lever? That's right, it's the same. In physics, work is always conserved on a simple machine. The input work and the output work will always be equal. So let's go on. Let's look at this. This is a pulley system. It's got a fixed pulley and a movable pulley, so it's a B and T, a block and tackle, B and T. Let's see if we can calculate the amount of work. So on this side, we're pulling down, and we're pulling the rope 2 meters with a force of 5 newtons. How much work is being done? 5 newtons times the rope goes 2 meters. So again, this time it's 10 joules of work. Okay, let's look at our box. Our box comes up, we'll say, from the floor, and it comes up 1 meter. The box has a 10 Newton weight, and so what's our work? 1 meter goes here, 10 newtons was the box, and so 10 joules is the work. Again, notice the output, which is here, amount of work, will always equal where the input work is being done. Work is always conserved in a simple machine, even a block and tackle. Okay, here's another one. Let's see if we can figure things out. If work in joules is the force, newtons times the distance. Let's see if we can answer some questions. Let's say we lift a box up this high. How much effort do we pull on the rope? Right here, right here, how much effort? Well, the box is 50 newtons, that's the output. So what's the input over here? Well, we remember this from our levers unit. Mechanical advantage always is output divided by input. So let's plug in our numbers. Output is 50. We don't know the input, but we know the MA, don't we? Sure we do. Count the number of ropes holding up the box. 1, 2, 3, 4, 5 ropes. You don't count this one because it's not helping hold up the box. So the MA is 5. So 50 divided by what equals 5? That's right, 10. So the input here is 10 newtons. Okay, how much work is done? Well, we don't know how much the rope is being pulled. We could find that. But we know over here on the output side that the box came up 5 meters and the box is 50 newtons. So F times D, force times distance, that is 50 times 5 meters would be 250 joules, J. Okay, so over here, the input side of the simple machine should also equal 250 joules. Well, we know the force, so 250 joules on this side equals the force, which is 10 newtons, times how much rope? Well, it would have to be 25 meters of rope on this side because this side has to equal 250 joules, just like the other side. So how much rope did we pull? Pull 25 meters, 5 times as much. Let's check this one out. The box comes up 1 meter. Oh, look, it's in kilograms. We need to convert it into newtons. So let's do that. On Earth, 1 kilogram is about 10 newtons. So if we have 200 kilograms, that's 2,000 newtons. 2,000 newtons for the box. And it comes up 1 meter. How much work? Well, we can find that in the output side. 1 meter, so force times distance, F times D. And D is 1 meter and 2,000 newtons. Love my writing, hey? And so the amount of work in joules is 2,000 joules. Okay, let's go back to mechanical advantage. That's easy. Let's check 1, 2, 3, 4 ropes. You don't count this one, so the MA is 4. So how much input? Well, MA is always output divided by input. Output divided by input. So let's figure that out. The output is 2,000. So we don't know the input, question mark, but we do know the MA because we counted the ropes. The MA is 4. So 2,000 divided by what would equal 4? 2,000 divided by 500 is 4. So how much effort is needed? 500 newtons. 500. Okay, it tells us that the rope's going 4 meters, and we know we're pulling with 500 newtons. So how much work is done on the input side? 4 times 500, the same as the output, 2,000 joules. And hopefully that gives you a good idea as to how to calculate work and the fact that work is always conserved in a simple machine.